Hello and welcome everyone. Today we're gonna continue following the Vulkan tutorial. If you remember from last time, we managed to create vertex buffers to hold our vertex data. And so we modified also our shaders to no longer hardcode vertex data, and we allocated memory for the vertex buffer. We filled it with our vertices from the transferring data from the CPU to the GPU. And we were able to modify some of the vertices data, so we could output different colors, for instance, on the triangle. So let me show you the current status. As you can see, we have something very similar to the Vulkan tutorial, and we were able to change one of the colors from red to white. And this is done in our application here, where we define our vertices. You can see here that the first vertex is white now, and we could change it to, for instance, we can modify it like this maybe. And if we run it, now we get yellow instead of white. So basically this was to prove that our vertex data is in fact used, and we are no longer hard-coding vertex data in the shaders. Here we're using two attributes, one for the position and another one for the color. And we pass these attributes to the fragment shader where they are being rendered. So I can show you the other shader. Here we just take one input from the vertex shader and we output that, adding one more component to the W. So today we will continue with the next chapter, which is about using staging buffers. So I'm not familiar with the concept, but we will get through it. So the vertex buffer we have right now works correctly, but the memory type that allows us to access it from the CPU may not be the most optimal memory type for the graphics card itself to read from. The most optimal memory has the property device local bit flag and is usually not accessible by the CPU on dedicated graphic cards. In this chapter we're going to create two vertex buffers. One staging buffer in CPU accessible memory to upload the data from the vertex array, and the final vertex buffer in device local memory. We'll then use the buffer copy command to move the data from the staging buffer to the actual vertex buffer. I see. Transfer queue. The buffer copy command requires a queue family that supports transfer operations, which is indicated using the DKQ transfer bit. The good news is that any queue family with graphics or queue compute bit capabilities already implicitly supports queue transfer operations. The implementation is not required to explicitly list it in the queue flags for those cases. We're not gonna do this challenge. Abstracting buffer creation. Because we're going to create multiple buffers in this chapter, it is a good idea to move buffer creation to a helper function. Create a new function, create buffer, and move the code in create vertex buffer, except mapping to it. So in this function we create the buffer where the size and the usage are parameterized. Then we get the memory requirements for that buffer. We also allocate memory for it using the properties that are also parameterized. And we are binding it as well. Okay, so if I try to find this part in our code, okay, create buffer, and let me get rid of this message. Basically we want all of this code except size, usage, yeah, basically all of these. Including the binding of buffer memory, we're gonna copy it and put it down here at the bottom. Create a buffer or vertex buffer. We need to add an unsafe log. And we can paste all of this. We're gonna rename this to just buffer. And then everywhere where I use it, buffer. I'm gonna stop printing the memory requirements. Also the vertex buffer memory, I'm gonna rename it to just buffer memory. And then we bind it for buffer and buffer memory. And if I remember correctly, we wanted to parameterize the size and usage. Let's use the same order of parameters that they are using. Pick a device size, the usage, which is BK buffer usage flags, BK buffer usage flags. The properties for the memory. Properties. And the last two parameters are references, but we are gonna just return them. So we can return in a tuple the BK buffer and the BK buffer memory. Is that the right type? I think so. It should be, yeah. BK memory, device memory, could be. Yeah, I think so. And then at the bottom of our function, we can just return a tuple, buffer and buffer memory. And now we can start using, for the size, we can get rid of the calculation that we were doing. Also for the usage, the properties are used, I think, for finding the memory type. So where do we call this? Find memory type, passing in the memory type bits and the properties. So yeah, this one can be properties. Let's get rid of the trailing comma. And yeah, I think that should be most of it. The only problem we have in here is that we don't have access to the device. So we'll add it as the first parameter. Now we should be good to go. So go back here and we can replace all of this with let vertex buffer is equal to create buffer, passing in the device. And what else? Oh, they even create a specific function for creating a vertex buffer. I see. Anyway, let's go one step at a time. So for the size, we can grab this. Then the usage is pk buffer usage vertex buffer bit. And the properties should be, what are we using for properties? BK memory host visible and host coherent. That's for the, wait a second. Yeah, let's still grab this from here. And later we will end up removing those. So now we can get rid of all of this code. And before we do some more refactor, let's try to run it. Make sure that it still works. And it doesn't. Oh, that's right. We not only return the vertex buffer, but also the vertex buffer memory. And we need access to the physical device as well. So add it in here. Looks that it's still working as it should. So good. Now the next step, if I'm not wrong, is to add one more function to create a vertex buffer, which will use the internally will use the create buffer. So let's do that. So let's call this one create vertex buffer. Problem is that we need to pass in all of these parameters around for now. So this one maybe can take the vertices as a slice of vertex structure. And in here we can call the create buffer. So we can call create buffer, passing device and physical device, which we'll need to add. The size is gonna be whatever we were passing on the create because the problem is that we need to clean up these resources. Right after creating the staging buffer, and instead of mapping the vertex buffer memory, we are mapping the staging buffer memory. We can use the buffer size that we have computed here. Buffer size. We copy the vertices to the map data, and then we unmap the staging memory, like so. And finally, we create a vertex buffer, but this time we specify the usage as transfer and vertex buffer. So here we can replace this again with buffer size, and down here, where before we were only using the vertex buffer bit, we now need to add this extra usage for transfer destination, because we're gonna transfer from the staging buffer into the vertex buffer. And the properties, I don't think we need host visible anymore. We just need device local. So these two can be replaced by this one. And what do we return from here? The vertex buffer is now allocated from a memory type that is device local, which generally means that we are not able to use map memory. However, we can copy data from the staging buffer to the vertex buffer. We have to indicate that by specifying the staging buffer and destination flag for the vertex buffer. Did I specify transfer source for the... Yeah. The staging is transfer source and the actual vertex buffer is the destination. We're now going to write a function to copy the contents from one buffer to another called copy buffer. Memory transfer operations are executed using command buffers just like drawing commands. Therefore, we must first allocate a temporary command buffer. You might wish to create a separate command pool for these kinds of short-lived buffers, because the implementation may be able to apply memory allocation optimizations. You should use command pool create transient bit flag during the command pool generation in that case. But here I think they are using just the same command pool. We need to somehow destroy the staging buffer and free the staging buffer memory. Right, because if I run this now, I'm gonna get, and I quit the application, I'm gonna get some validation errors that I'm not destroying the staging buffer and not freeing the staging buffer memory. So we'll have to deal with that, but let's implement this copy buffer function first. Up here, maybe add a function for copy buffer, and we're gonna take the source buffer, and the dest buffer. And do we need anything else? We need the size that we want to copy. Size. Okay, device size. Probably we'll need more things like the command pool and so on. But we'll see. So what do? We allocate a command buffer that is going to, where we're going to record the command to copy from one command to the other. And we need the device to create this, as well as some command buffer allocate info, which we can initialize directly here. Then we need the command buffer that we want to create. And we need to declare it first. Let new command buffer, some mutable null pointer. And let me see. Command buffer. PK command buffer allocate info. We need basically all of this. So For pnex, we can just pass in null. Cannot type today. The command pool is gonna just be passed in to us. The level is gonna be primary. Yeah, buffer level primary. And we just want one command buffer. So I think that should be all that we need. And I'm gonna start already adding the parameters that we require. We need the device as well as the command pool. And after we have allocated okay, this function can fail, so we can add a check for it. Oops. Right after creating the command buffer, we can start recording into it, which takes the command buffer and some bk command buffer begin info. And I think we don't take anything else. We have it down here. S-type, pnex, flags. S-type, it's gonna be command buffer begin info. Pnex, as always, null. Then flags, we want just one time submit, and p inheritance info can be also null. This one can also fail, so let's not forget to check for failure. Like so. And we'll have to end also the recording and command buffer. Takes the command buffer, just the command buffer. And this one also returns a result. We need to add this constant. We don't have it, looks like. So let's grab it from the Vulkan header. Okay, command, buffer, usage, grab all of these. And down here. Now we should have them. What else do we need? We start recording into the command buffer, and the only command that we want to issue is this vk command copy buffer. So we can place it in here. And this one takes the command buffer, the source buffer, the destination buffer. I'm guessing the size. I don't know what that one is, but we need a copy region or buffer copy. And this one is gonna take source offset, test offset. Well, in fact, let's add the binding for this function already, because I don't think we have it yet. So down here, add the bk command copy buffer, takes the command buffer, source buffer, destination buffer, region count, and p regions. I'm guessing we can copy only partially buffer, and that's what this will allow us. So we need to add this bk buffer copy structure, the one without the two, this one, which seems to be simple enough. Extract, add it in here, abstract, bk buffer copy, takes the source offset. So yeah, this will allow us to specify if we want to copy from the start of the source buffer or if we want to start after a few vertices. Like in case where you have multiple models inside the same vertex buffer, you can choose to copy only a subset of the models or something like that. These need to be pub, dest offset, and finally the size I want to copy. I think this can be all 0, and the size is gonna be the size that was passed in as parameter. Yeah, right. So we don't even need we don't even need to specify it. So now where do we call copy? The command buffer only contains the copy command, so we can stop recording right after that. Now execute the command buffer to complete the transfer. So right after ending the command buffer, we need to submit it to the graphics view. And we're just gonna have one submit info struct. And for the fence, we don't need a fence. And this one can fail. And for the submit info, we need the S type. gonna grab all of these. And paste it. But modify with only what we need. I think we won't need any semaphore. So all of these can be zeros and null pointers. The command buffer, we actually need one. And we also don't need any semaphore to signal. So I would expect this to work. The only thing is that we don't have the graphics queue available inside this function. So how do they do it here? Well, apart from queueSubmit, we wait right after submitting to it. Graphics queue. And then we can free the command buffer. Okay. It's not helping me here. Okay, free command buffers. Takes in the device, command pool, one, command buffer. Don't forget to clean up the command buffer used for the transfer operation. Right, so the staging buffer is directly destroyed inside the create vertex. I see now. So this one needs also the graphics queue. Okay, queue. We don't have the BKQ white idle, looks like. We don't. But we can add it in here. And it just takes the queue. I'm guessing at least. BKQ wait idle. Yep, I was right. So now are we good? Let's check. BK free command buffers does not exist. Didn't we add this one? BK free no, we don't have it. Okay, all okay. So let's add it in here. Free command buffers. Free command buffers. Takes in the device, the pool, the amount of command buffers to free, and the pointer or array to the command buffers. Let's see if that did the trick. And cool. Now we're just getting a few warnings, but we should be able to get rid of them very soon. So back to our copy or create vertex buffer function. After we have created the vertex buffer, in here we can invoke this copy buffer, take the device, command pool, graphics queue. Source buffer is the staging buffer. The destination should be the vertex buffer. The size is the buffer size that we computed. And I think that's all. What am I missing? Well, of course, some of these parameters are not available yet, but device, physical device, graphics queue, and command pool. Looks like now we're good. And of course, free the memory for the staging buffer and destroy the staging buffer. Free the memory for the staging buffer memory. No allocator used here. And pk destroy buffer device staging buffer and no allocator. So now we shouldn't get that complaint about these two not being used. But we modified the signature for the create vertex buffer, so vertex buffer now takes also after the physical device, we take in the graphics queue and the command pool. Let's check if we compile, and we do. Let's run it and see if it's still working. And it is still working, very nice. And if I quit, we don't get any validation error, so we managed to do all of this without any problem. So let me read the conclusion. It should be noted that in a real-world application, you're not supposed to actually call bk allocate memory for every individual buffer. The maximum number of simultaneous memory allocation is limited by the max memory allocation count physical device limit, which might be as low as 4096 even on high-end hardware like an NVIDIA GTX 1080. The right way to allocate memory for a large number of objects at the same time is to create a custom allocator that splits up a single allocation among many different objects by using the offset parameters that we've seen in many functions. You can either implement such an allocator yourself or use the Vulkan memory allocator library provided by the GPU Open. However, for this tutorial, it's okay, yeah. All right, so let me see the changes that we did. And we moved this all into functions. Okay, so let's add everything and commit it as use staging buffer for transferring vertex data. Sounds good to me. Push this. All right, so let's continue with the next chapter. Which is about index buffer. The 3D meshes you'll be rendering in a real-world application will often share vertices between multiple triangles. This already happens even with something simple like drawing a rectangle. So yeah, these vertices here in the two corners are shared by the two triangles. So we can use an index buffer to store indices into the vertex buffer, and that way we can avoid duplicating vertices. Let's see how we do that. Index buffer creation. So first we modify the vertex data, right? We copy this for reference. Vertices. Up here. So we already have we'll close this one. The first one is going to be position minus 0.5 minus 0.5, and the color is going to be red, sorry. The second one needs to be modified to 0.5 minus 0.5, and it's gonna be green. The third one is at the proper position, but it will be blue. And the last one, I think it's also correct, but we're gonna change the color to white. So get rid of this. So now we have 4 vertices instead of 3, but we're gonna need an index array. Yeah. Indices. Let's make it a vector of U16. And here are the indices. What are you complaining about? Nothing. Cool. It is possible to use either U16 or U32. For now, we're gonna use less than 65,000, so we can use U16. Yeah. Just like the vertex data, the indices need to be uploaded into a BK buffer for the GPU to be able to access them. Define 2 new class members to hold them, blah blah blah, and then a function create index buffer. So let's do that directly. Create vertex buffer, and after this one we can have create index buffer. In fact, I'm gonna copy the whole function and rename it here. We're gonna take a slice of U16 instead of vertices. And then what other modifications do we need? The buffer size is gonna be the size of the... we could use this also for the vertices, so we don't need to hardcode the type. So the size of the first multiplied by the length, like this. Then we create a staging buffer with transfer source, host visible, host coherent. Looks good to me. Then we need to copy the indices, not the vertices, as mute U16, and this is gonna be indices. Then we create a buffer with transfer destination and usage index. So this one is now gonna be index instead of vertex, and also device local. Rename this to index buffer memory. And for the copy, we want to copy from the staging buffer to the index buffer. Oops. And for the return, we now return the index buffer and the index buffer memory. So let's see, we didn't get anything wrong. Looks like we don't. I'm gonna take the opportunity to also change the one for vertex. Instead of using the size of, I'm gonna use the size of bow. That way, if we change the name of the vertex structure, this will still work, I think. And now after creating the vertex buffer, we're gonna create the index buffer. So if we search for create vertex buffer, we can copy this over index, index buffer, except now we pass in the indices. I forgot change the signature. Did I? No, I didn't. So, and when we destroy bk destroy buffer, when we free the memory for the vertex buffer, we also want to free the memory for the index buffer and destroy the index buffer, like so. Okay, looks good to me. And now, how do we use this newly created index buffer? We need to make 2 changes on the create command buffers. So right after binding the vertex buffer, we also need to bind the index buffer. Okay, bind vertex, command bind vertex. We also bind the index. We pass in the index buffer, 0, and the type either U32 or U16. Let me grab the declarations, signature for this function. No, we can only bind 1, looks like. Command buffer, offset, and index type. Probably the index type is an enumeration or something. That's right. So grab it. And add it here at the bottom. We will not be able to have 2 names for the same variant. So something like this. Check if it compiles. A local variable, command buffer, I think we use the ds. Command buffers. Great. Great. And now, just binding an index buffer doesn't change anything yet. We also need to change the drawing command. So we need to remove the command draw and replace it with a command draw index set instead. Makes sense to me. So and this takes the command buffer, and what else? The length of the indices array. So indices.len as U32, I'm guessing, and then 1 and 3 zeros. 1, 0, 0, 0. Let's comment out the regular draw, and let's also add, oops. Let's copy this from there. So what else do we take? Index count, u32, instance count, first index. So we can start from an index other than 0. Vertex offset. And this one is actually an I32. Finally, first instance, u32. I think I got that right. Let's give it a shot. And there we go. We have a rectangle now, using indices instead of just having the vertex buffer. Very nice. So let's see the changes that we introduced. Not that many after all. The biggest one is the creation of this create index buffer function, but that's okay. So we can commit all of this. Use indices for rendering. Push this. And shall we go to the next chapter about uniforms? I'm tempted. Yeah. Yeah, let's start with it at least. Let's go for it. So, uniform buffers. We are now able to pass arbitrary attributes to the vertex shader for each vertex, but what about global variables? We're going to move on to 3D graphics from this chapter on, and that requires model view projection matrix. We could include it as vertex data, but that's a waste of memory, and it would require us to update the vertex buffer whenever the transform changes. The transformation could easily change every single frame. The right way to tackle this in Vulkan is to use resource descriptors. A descriptor is a way for shaders to freely access resources like buffers and images. We're going to set up a buffer that contains the transformation matrices and have the vertex shader access them through a descriptor. Usage of descriptors consists of 3 parts. Specify a descriptor layout during pipeline creation, allocate a descriptor set from a descriptor pool, bind the descriptor set during rendering. Yeah, and these are the 3 steps. The descriptor layout specifies the types of resources that are going to be accessed by the pipeline, just like a render pass specifies the types of attachment that will be accessed. A descriptor set specifies the actual buffer or image resources that will be bound to the descriptors. Just like the frame buffer specifies the actual image view to bind to render pass attachment. The descriptor set is then bound for the drawing commands, just like the vertex buffers and frame buffer. There are many types of descriptors, but in this chapter we'll work with uniform buffer objects. We'll look at other types of descriptors in future chapters, but the basic process is the same. Let's say we have the data we want the vertex shader to have in a system. The binding directive is similar to the location directive for attributes. We're going to reference this binding in the descriptor layout. The line with GL position is changed to use the transformation to compute the final position in clip coordinates. Unlike the 2D triangles, the last component of the clip coordinates may not be 1, which will result in a division when converted to the final normalized device coordinates on the screen. We have a 0 and 1 here. Yeah. The next step is to define the UBO on the C++ side and tell Vulkan about this descriptor in the vertex shader. Okay, so we need some kind of structure holding three matrices. So we had a vertex in here, and now we're gonna this uniform buffer object. This has the model. And what should we set as the type? I'm gonna create a matrix for type model view and projection. Or maybe we can just add a type alias for the mat4 type to be an array of 16 floats, right? Because it's a 4x4 matrix. So this could work also. Let's see if we can do that. We can exactly match the definition in the shader using data types in GLM. The data in the matrices is binary compatible with the way the shader expects it, so we can later just memcopy a uniform buffer object to a BK buffer. We need to provide details about every descriptor binding used in the shaders for pipeline creation, just like we had to do for every vertex attribute and its location index. We'll set up a new function to define all of this information called createDescriptorSetLayout. So let's see, where do we have our BK create pipeline? It was BK create graphics pipeline. This one, do we have it in a function? Yeah. Create graphics pipeline. And we call it integrate swap chain. As well as directly in main. We created the render pass and then so maybe I will start putting this code here for now, and if I need to, maybe I will extract it later on. So how does it work? We need this BK descriptor set layout binding. And where is it used? Okay, so ultimately we call into this BK descriptor set layout. So let's start there. Oops. Let's grab the definition for this one. Because I don't think we have it so far. Where can we place this? Reset fences, semaphores, not here, buffers, pools, frame buffers, pipeline, maybe after pipeline, or no, maybe before pipeline. And before pipeline layout. So yeah, maybe here. PK, create, descriptor, set layout, text the device, the creation info, and the allocator as usual. And gives back the set layout by pointer. And it also can fail, so it returns a BK result. And I can see already here that we have a function to destroy it, so I will add it to clean up. Okay, destroy the scriptor set layout. There we go. So we need this BK descriptor set layout create info. I can type. Here it is. And I'm gonna place it right after BK shader module create info. Yeah, here it's fine. Public struct, BK descriptor set layout create information. Text the usual S type and P next. Flags. Binding count. And the actual bindings. And what is it's up here. So a BK descriptor set layout binding consists of an index indicating the binding I'm guessing this is the binding keyword that we use in the shader. Then we have a descriptor type, which is its own type. Descriptor type, descriptor count, stage flags, immutable samplers, looks like all of these types except VK descriptor type are, we have them. The descriptor type, it's an enumeration. What did I do? Make all the variants available. Okay, descriptor type. We also need to add the flags. And I think that's mostly everything. Let's double check. All right. Did I not save? All right. Now, how do we call this? We pass in the device. And one of those descriptor cell layout info with all of these fields. So we'll finish the field later. We have also the allocator. Now we just need to fill all of the descriptor cell layout, create info. Okay, descriptor cell layout, create info, which basically is the flags, binding count, and the bindings. I think that we're just gonna have one binding, so we only have one uniform and no flags. So flags can be 0. And the bindings is going to be, let me keep this. Descriptor cell layout binding. This one takes all of this. think the binding is 0. Yeah, binding is 0. Descriptor type is a uniform buffer. Descriptor count, we have only 1. Stage flags, we're gonna use it on the shader, vertex shader. And the sampler, it's optional, so we don't need to fill it in. So we can pass null in here, format it, and now we're missing something. Just a couple of warnings. Yeah, just a couple of warnings about unused, these structs are not used, which is fine for now. So let's see what else we need. We need to clean this up. So right before we clean up image view, in between image views and render pass, okay, destroy render pass for image view. Where do they do it? After swap chain. So let's do the same. And let's give it a try, just to be sure. So there we go, we can still see our rectangle, and if we now exit the application, we don't get any validation errors. So we're good. Next, what do we need to do? In the next chapter, we'll specify the buffer that contains the UVO data for the shader. But we need to create this buffer first. We're going to copy new data to the uniform buffer every frame, so it doesn't really make any sense to have a staging buffer. It was just add extra overhead in this case and likely degrade performance instead of improving it. We should have multiple buffers because multiple frames might be in flight at the same time, and we don't want to update the buffer in preparation of the next frame while the previous one is still reading from it. Thus we need to have as many uniform buffers as we have frames in flight, and write to a uniform buffer that is not currently being read by the GPU. To that end, we add new class members, uniform buffers, and uniform buffers memory. And right after index buffer, we can create the uniform buffers. So I'm gonna take a quick break before I tackle this. So yeah, I will see you in 5 minutes. I'm back. So we were checking this. We were about to add the uniform buffers. Here they are doing it after creating the index buffers. So let's check out that part of the code. Create index buffer. So we want to create the uniform buffers down here. And yeah, we need to have one uniform buffer for every frame that we can have in flight. Properties, which are gonna be host visible and host coherent, the same as the staging buffers, if I remember correctly. And this will give us a uniform buffer and a uniform buffer memory, which we can then push into the respective vectors, right? I think I changed my mind. The uniforms buffer, uniform buffers, push uniform buffer, and uniform buffers memory, uniform buffer memory, like this. And size of needs to be from memory or from core. Do I have size of? Yeah, from mem. And we don't need this I variable, so we can just have underscore. And on the cleanup, decay, destroy, index, destroy, kind of type today. So here, in fact, we can reuse this loop that also loops for the max frames in flight and be sneaky. So we want to free the uniform buffers memory at index I, and then we want to destroy the uniform buffers at index I. Let's see if that works. It does. We're going to rewrite a separate function that updates the uniform buffers with a new transformation every frame. So there will be no BK memory here. The uniform data will be used for all draw calls, so the buffer containing it should only be destroyed when we stop rendering. We're going to write a separate function. The uniform data will be used for all the draw calls, so the buffer containing it should only be destroyed. Since it also depends on the number of swap chain images, which could change after our recreation, we'll clean it up in cleanup swap chain. Yeah, that it's what we did already. And we need to modify, oh fuck. We need to call it also when we recreate the swap chain. So this code in here should also be called when we recreate the swap chain. Let's not do that for now. Let's see. We'll do it when we need to. Then updating uniform data. Create a new function, update uniform buffer, and add a call to it from draw frame right after we know which swapchain image we are going to acquire. So I think here they are creating the whole matrices with GLM. Then they map the memory and they write into it. Using a UVO this way is not the most efficient way to pass frequently changes values to the shader. Let me take a look at the source code they provide and take a look at this update uniform. Where do they call it? Before reset fences. Okay. So in here, they do is they create a new UVO buffer object every time, compute the matrices according to the current time, and then just map the memory and copy the values from the UVO. I think we can do that. Let me grab PK. Let's grab one of those. Paste it in here. So we're gonna map uniform buffers memory for the current frame. The size is gonna be the size of our uniform buffer object. And then we just copy. Here again we need this. So basically we will have an UVO here, uniform buffer object. It's gonna have a model, a view model. It's gonna be 0 times 16 for all of the respective model or projection view model. all initialized to 0 for now. This needs to be columns. And then we copy this data here. SVK device size. And when we unmap, we need to also unmap the proper memory. Uniform, buffers, memory at the current frame. I think that should compile. 1, 2, 3, 8. Create buffer. What? When did I replace this? This should be PK create buffer, right? I don't know what happened here. That was really weird. Let me check the diff. Introduce this struct in the shader and in main. We created the descriptor cell layout, the uniforms, and then we update the uniforms here. We clean up, and then we also have bindings. Okay, I think I did a typo somewhere and that got replaced. So if I run this now, maybe we won't see anything. Segmentation fault even. Oh man. Update. Okay, map. What did I do wrong here? I want to go to grab this line, go to main, and print the size of this. Right after that, we can just want to see the size of this. 192. And we have 16 floats times 3 matrices. and each float is 4 bytes. So yeah, it's 192. So that's correct. So are we not mapping it right? Or are we... Maybe current frame, maybe we're not creating enough uniforms? That could be. Try to debug this, but I have to go real soon, so it's a shame. Why is it so slow? Okay, we already got the segmentation fault, backtrace, align 537. So it's in the copy. It's in the copy. So there's definitely something fishy here. I want to check again the Rust man copy. Need to check the signature again. Not this one, but the one from the standard library. Copies count times size of t bytes from source to destination. So this should be one. Now I see. This is a count, not the number of bytes. Let's see. We should still not see anything because I need to get rid of this debug. Right again. And we're back to seeing the rectangle. It's not clear to me why do we still see it, because did I not compile the shaders? I think I forgot to compile the shaders. If I compile the shaders and run it again, I still see the rectangle. How weird. So we passing everything as 0. And here we are, in theory, multiplying 0 times 0 times 0 times the position. Shouldn't this be 0 as well? Oh, did I not write the shader? Compile it again and run it. Huh, yeah, that's what I was expecting. Shader uses descriptor slot 0, but not declared in pipeline layout. So did they say anything about this in the tutorial? Do they mention anything about the pipeline thing? Pipeline layout. We need to specify the descriptor cell layout during the pipeline creation. I forgot about this. So let me go back to main. Yeah. So we got one set layout. That right? Yeah. And this one should be descriptor set layout. I forgot, or I didn't see this part. And we need to pass in, this is in a function, right? Why do we have it 3 times? So here we have it available. But in here, oh, fuck. In recreate swap chain, we also need it. Oh, fuck. Let's comment this out. Do we recreate the swap chain at all? Probably yes. Probably yes. Extensions. I don't see that we are recreating it. So I'm missing something. I really need to go. I think. Do you have any BK command in here? I think they are going to explain this later. I think we might be missing something here. Do they use any command here? Yeah. Okay, I need to leave now, so I will call it a day and I will resume from this point. So thank you all for watching and I will see you next time. Bye.